Today we will try to understand the thermodynamic properties of an ideal monoatomic gas. Uh, we'll take the example of monoatomic gases, for example helium, neon, argon, etc. There are basically only translational and electronic degrees of freedom. So the partition function molecular partition function is given by that means if we write the molecular partition function for the ideal monatomic gas by Q, it will be simply equal to the partition function from the translational degrees of freedom and electronic, that means the electronic partition function. So this will be our equation number 1. Now but here the electronic partition function is basically equal to the G0, that is the degeneracy of the electronic ground state. That means we can simply write then the molecular partition function as G0 into Q translation. Or we can put the value of translational partition function, which is basically equal to, if we know from the previous knowledge that this translational partition function is basically equal to 2 pi m kt upon h square whole to the power 3 by 2 into volume. So this is basically our translational partition function here. So we will take this value and introduce in equation second, that means Q will be simply equal to Z0 into 2 pi m kt upon h square whole to the power 3 upon 2. This will be our equation third. Now we will take this G0 equal to 1. This is basically for most atomic systems, this degeneracy is basically equal to 1. Most atomic systems. That means we are left with only the translational partition function, that means 2 pi m kt upon h square 3 by 2. So this will be our equation number 4. Now we know the internal energy, that is U, in terms of partition function is related by this expression. We have already derived this in the previous video lectures. If you have any doubt, you can watch those lectures and come to here. So it will be dou ln q upon dou t, but this is at constant volume. So equation 6. What we do here now, we will simply introduce the value of equation 4 into equation 2nd. So it will be equal to nr t square dou by dou t of ln 2 pi m kt upon s square whole to the power 3 by 2 into volume. So this is basically our equation. Now we will simply differentiate this part here. So we can simplify this part as nRT square. First we will write this differential outside, and we will first separate these terms. We can write ln of 2 pi mk, because these are all constants, so we will write these separately. 3 by 2, we are basically this internal energy is at constant volume, so we will also multiply it with volume, plus we are simply taking only the temperature term outside, so it will be ln of t raised power 3 by 2. Now it is very simple. If we differentiate this part with respect to temperature, so it will be equal to 0 constant 1. So we can write, we can separately write these as dou upon dou t ln of 2 pi m k upon s square 3 by 2 into volume, plus again we will differentiate this with respect to temperature 3 by 2, but this is ln. Okay, so obviously this term will be equal to 0, so this will be equal to 0, this whole term. If this is equal to 0, so we can write the relation then, nRT square dou upon dou t of, this is log m raised power n, so we can simply take 3 by 2 outside, so we can write it as 3 by 2 dou upon t, but it is ln of t. Okay. So we know a differentiation of ln of t will be equal to 1 upon t, so it will be equal to nr t square 3 by 2 into 1 upon t. Simply differentiate ln of t with respect to t temperature, so we will get this relation. So now this t and 1t will cancel, so that means the internal energy will be simply equal to 3 by 2 nr t. So this will be our relation for internal energy for an ideal monothermic gas. So we can now also calculate the or derive the molar heat capacity, which is simply but at constant volume. Okay, CV. So this CV, that means the molar heat capacity at constant volume, is simply related by this expression, change in internal energy with respect to temperature but keeping the volume constant. So what we do here, we will simply introduce this value here. So if it is equation number, this is 6, this will be 7, 8, 9, 10, and we can write it as 11, 12. So we can put the value of equation 12 into this. So we can simply write dou upon dou T of 3 by 2 of N R T. Okay, but this is at constant volume. So as N is number of moles, it is constant, R is gas constant, so N 3 by 2 is constant. We will take this outside, so we can simply write 3 upon 2 NR dou T upon dou T, which will be equal to 1. So that means the molar heat capacity at constant volume will be equal to 3 by 2 NR. Also remember, you can write this in terms of total number of molecules and Boltzmann constant also, as Nk is equal to Nr. We can write Cv is equal to 3 upon 2 Nk. Remember here, N is total number of atoms or molecules, whatever may be the case, and N is number of moles. So you can write this equation as also. This will be our equation 13 and this is 14. Now we will try to derive the entropy of an ideal monoatomic gas. So we know this entropy is related by this expression, and R ln of, in terms of partition function, Q upon N plus T 2 upon 2T ln of Q plus 1. So remember here, this is basically Q is here simply the partition function. So we will introduce the value of simply the translational partition function in place of Q. So we can write S is equal to NR First it will be ln of, in place of q we will have this 2 pi m kt upon h square raised power 3 by 2 into volume, and this n, so it will be divide, it will be in denominator. Okay, so plus t, this term now rho upon dou t ln of, again the translational partition function or the partition function for a monatomic gas, 2 pi mkt divided by square raised power 3 by 2 into v, and it is plus 1. So this will be the overall equation here. Now first what we will do, we will first differentiate this part only. We will take this part and try to find its value. Here if we solve this part, we can write it here, t rho upon dou t, and we can write it in terms of, we will take the temperature and write it separately as a term with ln. So we can write it ln of t raised power 3 by 2. So it will be simply log m into n, we will simply write log m plus n. Okay, so it will be natural log of the remaining term here, 2 pi m k, this is also constant, as square upon 3 by 2 into volume. This is at constant volume, so v will be also constant. So we can write this part as this one. So obviously if we differentiate this much, so we can write it as dou upon dou t, so it is log m raised power n, we can write it as 3 by 2 ln of t, or simply we can write it as this way also, t 3 upon 2 dou t upon dou ln of t upon dou t. Because this is constant, we will take it outside, plus this term. So it is now the differential of this whole term, it is ln of 2 pi m k upon h square 3 by 2 into v, okay, multiplied by this term. So obviously this will be simply equal to 0, this term, because here this will be equal to 0, differentiation of constant will be simply equal to 0. So we are left with this term only. So we know we can write it in as 3 by 2 t, differentiation of ln of t will be simply equal to 1 upon t. So obviously this t and t will cancel, so we got the value 3 by 2. So that means here the value of this part is simply equal to, this part is equal to 3 by 2. So we can rewrite this relation as S is equal to NR, the remaining term is ln 2 pi m kt upon s square 3 by 2 into v upon n, plus we got the value of that part equal to 3 upon 2 plus 1 is there, so this will be our equation. So we can simply write this part equal to 5 by 2. So here this part will be equal to 5 by 2. So that means we can simply write this as nr 5 by 2 plus this term ln 2 pi m kt upon s square 3 by 2 into v upon. So this can also be further simplified, as we know for an ideal gas PV is equal to nRT, or for 1 mole of an ideal gas we can write, if n is equal to 1, so we can write V is equal to RT upon P. Also the gas constant, that means the R, is related to the Avogadro's number by this much, Boltzmann constant into Na. This is Avogadro's number. Okay, that means here basically we will try to find the value of V by N. So this V by N will be simply equal to, we have value of R equal to this, that means we can write V by N will be equal to, we have value of V is equal to RT upon P. In place of R we will write KNA. R, first we will write that RT upon P is here and simply divided by N, so we will write this N. So this N is total number of the atoms or molecules in the system, and this is Avogadro's number Na. Okay, don't confuse it with the Na. Okay, so we can write it as K in place of R Na upon T divided by, so here it will be Na. Okay, so it will be Na into P, so that means this will cancel, it will be equal to KT upon P. That means we can write the relation, then S is equal to nR 5 upon 2 plus ln 2 pi m kt upon h square on 3 by 2 into kt upon P. Okay, basically what we are doing here, if you remember the previous one, we are taking nR is equal to nk, but this n is basically number of molecules upon Avogadro's number. into R, which is equal to Nk. So remember this also. Okay, so that means we got this relation. But what we want this 5 by 2 in terms of natural, that means in terms of ln. It is very simple to turn this 5 by 2 into ln of, so we can write 5 by 2 equal to, we will multiply ln with exponential, so it will be simply upon 5 by 2. So that means 5 by 2 can be written as ln of e raised power 5 by 2. Okay, remember this is very important point here. So that means the now this relation can be written as nr in terms of 5 by 2, we can write ln and multiplied by exponential 5 by 2 plus this is ln of 2 pi m kt upon h square whole power 3 by 2 into kt by p. Okay, but we know the thermal de Broglie wavelength lambda is basically related by this expression, that means h square upon 2 pi m kt raised power 1 by 2. So what we do here, we will introduce this value into this equation. So s will be equal to nr, and we will take this will be log m plus log n, or we can write it as log m by n. That means if we write ln only, it will be first this term e raised power 5 by 2 multiplied by kt, and in place of h square 2 pi m kt raised power 3 by 2, we will write lambda q. Okay, that means we can write in place of this lambda, and but it is raised power 3, so it will be lambda cube, and p is there, so it will be multiplied by p. So this will be our final equation. This is very important relation, and this is known as Sacco-Tetrode equation. This is very well known equation called Sacco-Tetrode equation. Now if we have found this Sacco-Tetrode equation, we can also expand this. On expansion, simply we will give the ln back to the respective terms and introduce the value of this lambda, that means 2 pi m kt upon h square is for 3 by 2 again. So we will get this relation, simply s will be equal to nr this, if you multiply ln and e, it will be again 5 by 2 5 upon 2 plus here 1t is outside and 1t will be inside, that means ln of t raised power 3 by 2, that will be equal to 5 upon 5 by 2 ln of t, because ln of t raised power 5 by 2 will be equal to 5 by 2 ln of t, and this is in divide, so it will be minus ln of t plus, again k is here, 1k will be of this lambda, that means kt raised power 3 by 2, but that is in ln kt, so we can write it as plus 5 by 2 ln of k plus 3 by 2 ln of 2 pi m, and minus this is lambda cube, that means it is having h square in the denominator, but 3 with respect to and power 3 by 2, 2 and 2 will cancel, that will be h cube. It will be minus ln h cube, that can also be written as 3 ln h, that means Planck's constant h here. So you can use simply this equation, suppose this is equation A, you can use this, and simply first we have given ln back to e, it will be 5 by 2 here, and it will be ln of 2 pi m, we have written that outside, but it is ln of 2 pi m to the power 3 by 2, that will be log m raised power n, so it will be 3 by 2 upon ln of m. Similarly, this is in divide, this s square and 2 will go, and it will be h cube, but it is in division, so that is why it is minus. Okay, minus 3 ln h, or you can write minus 3 ln h cube, and 1 t k is outside and 1 is inside, it will be k raised power 5 by 2. 1 t is inside here, 1 t is outside, so it will be t raised power 5 by 2. That is why I have written here 5 by 2 ln of t and 5 by 2 ln of k. I hope this is very simple setup here, you can do it. Okay, so that means we got this relation, but this is the these are basically expanded terms here. Now we can substitute the values. Sometimes we can substitute the values of constants here, suppose, and calculate the total value. Suppose 5 by 2, this is constant, plus 5 by 2 ln k, this is also constant because this is Boltzmann's constant. Okay, plus 3 by 2 ln of 2 pi only, not m, because m can change, so 2 pi is constant, minus this will be again constant as it is a Planck's constant, so 3 ln of h, ln of h, Planck's constant. So this comes out to be negative 0.5055. So if we use this value and introduce into equation this, suppose b, so we can write s is equal to nr 3 upon 2 ln m plus 5 upon 2 ln of t minus ln of p minus 0.5055. You can take the standard entropy as well. If suppose now if this P is equal to 1 atmosphere, so ln of 1 will be equal to 0, so this term will be equal to, this term then will be equal to 0 if you introduce this condition. So you can write standard entropy then NR 3 upon 2 ln of m plus 5 by 2 ln of t minus 0.5055. If temperature is also given, so you can introduce the value here and calculate the standard entropy.